Okay guys, this is your lecture for Tuesday the 21st, and I'm going to try and combine two of them into one because I think that the concepts can be pretty easily explained in just a short period of time. So the first one we're going to talk about is the work done by friction. After this we're going to go over power and explain that, but this one will just be real quick. Work done by friction. What we've established so far is that the work equals a force. Well, we'll do this. Work is force times is the integral of F dot dr. The force times our differential of our displacement changing, and the sum of all of those as we progress over time. And we also know that work is our change in kinetic energy, and so kinetic energy, remember the kinetic energy is it is energy due to a motion's mass, due to a moving mass. Energy due to moving mass. Well, I'm going to try and move that around a little bit. There. Is energy due to moving a mass? Well, if we have, okay, and we've already established, if we have this mass here, then it's right, and we've got a surface, and so we'll draw our surface down here, and we've got a crate on it, and we've got a force pushing on a crate, right, and the crate's got some wheels, right, and if it starts off with initial velocity equals 0 and it travels over some distance, delta x, and it winds up, if it winds up here, right, it winds up there after it's, now it's moving pretty well, and it has this final velocity, v equals v, that our kinetic energy is going to, and here's a force over here, and so we have this force, and it's pushing into our object that we will have given it some kinetic energy, that our kinetic energy is going to equal our force times our displacement, and which is also equal to, so it's our change in kinetic energy, and that is equal to the work that we did on it. Well, what if we put our crate on a surface that has friction? So let's take our crate, and instead of it being on wheels now it is actually touching the surface. Okay, and we're going to give it an initial velocity. We're going to give it an initial velocity equal to, v. Okay, and so it's pretty significant. And then we push it, but we let it slide. We let it slide to a stop. All right. So let me go back here. There we go. And we let it slide to a stop so that our v final equals 0. Well, what happened here? Okay, and where did the energy go? Well, let's draw a force body diagram on this bad boy. So we're going to have a mg here, and we're going to have a normal force there, and those are balanced. But then if we're pushing in that direction, we're going to have a friction force down here on the bottom of kinetic friction that's actually going to be sliding, and that force is going to be acting opposite to the direction of motion. And so what we're going to get is our work is going to equal our friction, because that's the force acting on it, times delta x. Well, we also know that our friction is in the opposite direction to our displacement, and that winds up giving us a negative value work is going to equal this negative force F delta x for our change in kinetic energy. And if it comes to a stop, which should make sense, that if we take all of the kinetic energy away, that the work done by friction on the object would be negative. So that's really what we boil down to with friction. However, friction can also do positive work. This is what we just did is the standard definition of it, but or the what you'll usually see. But friction can do positive work, and I want you to consider a dragster. Okay, so here's the big wheels, and it's got the spoiler up on it, and right, and it's coming down here, and then it goes out, and it's got the little bitty wheels up in front, and a little spoiler out here. Comes down. He's got the big old roll bar back here, and it's got the little roll bar here, and the dude with the helmet, and he's driving. Okay, when this takes off, okay, now the best dragster drivers do this. When they start their car, when the light flashes green, they ride the edge of static friction with the car, because down here, right down here, we want to have static friction. And our static friction is actually going to push the car forward, because the tire wants to rotate that way, and so friction acts in the opposite direction. Now, of course, we have the other forces acting on it, so we have mg and we have normal acting on our dragster. But the big thing is our static friction that comes from our rear tires. If the best drivers will ride the edge where their force, this force turning this way, is equal to the static friction. And if it gets too fast, then it changes into sliding friction, and that's where you start seeing, billowing smoke puff out around, around the tires, and you start seeing the tires get all big. And when that does happen, you will still increase the kinetic energy of the car, but a lot of that energy is going to get dissipated into heat at the contact of the road and the tire. And the tires will get really, really hot, and you might even catch flames sometimes. It's a pretty spectacular scene when a dragster's tires catch on fire. But the best drivers don't do that. They ride that edge, they ride that fine line between maximizing their torque of the wheel and their static friction moving forward. So, what your book is going to tell you is that this heat right here this heat is given by it's called the delta E internal heat of the system. But we've all taken chemistry before, and we know it as Q. And yes, this is Q of the Q equals mc delta T fame, and that's heat, and it just goes into increasing the kinetic energy of the molecules of the road and of the tire. And if you remember that the increased kinetic energy of if we increase the average kinetic energy of the molecules in the system, that's really just increasing the temperature. And the way you increase the temperature of something is by adding heat to it. So that's what the book is talking about with E internal. Okay, so that's about it with friction. Um, there's going to be there'll be an assignment for that, accompanying that, but it's also going to go with the next thing we have, which is, oh, that's not good. Oh, that's really not good. Hmm. Well, I'm glad I preserved that. Um, I just need to go back a couple pages and we'll start with our power. So here we go. Okay, we're going to start with power, and power is the rate at which energy is transferred into or out of a system. Okay, and it's also known as, well, that energy that is transferred in or out of a system is also the change in the energy. Well, power then is this delta E divided by delta T, and this, okay, and it takes time. So for example, some examples of this, it takes time to boil water, or it takes time to get a vehicle up to speed. Okay, now remember, when we talk about deltas, it usually means the average change. But if we take a look at the units of this, is delta E. Delta E is, well, if we take a look at the units of uh, delta E over delta T, then we're going to get joules per second, and this joule per second is equal to a watt, and this is a unit that you've heard of before. Okay, now, and it's given the symbol of W. Okay, but don't, however, confuse it with work. This is a unit. Make sure that you're paying attention to the context. Now, again, the delta E and delta T gives us our average power. But whenever you see deltas, you should know it's coming. If we do this instantaneously, we take the limit as that delta T equals 0. Delta T approaches 0. Delta E over delta T becomes dE dt. Dun dun dun. Okay, so remember, work, okay, equals FDR, or the force times our differential displacement. And that leads to a dW. Okay, but if it's over that dr, then that's really just the differential change in work equals our differential equals our F times our dr. So if we have our, variable force, and we have our, when we divide it all up and we take all the individual pieces and we find this, the force of R times our dr, okay, is really just, and the time that it takes is our dW over dt. So it's really just F times dr, F dot dr, which is work, over dt, but, okay, that would be our power, dW dt. But what's dr over dt but velocity? So let's go back for a sec here. Okay, so let this sink in for a minute. Okay, that this little teeny tiny amount of force times distance, this work right here, if it takes place over time, okay, that's going to give us our dW dt, but dW dt is equal to force times dr dt, and dr dt is our velocity. It's the rate of change of displacement over time. Okay, so think about pushing our crate that already has a velocity. Okay, if we we push this over a distance. And all of a sudden our cart's going to be moving pretty well. Okay, and that means our power is going to equal our dE over dt. But we can manipulate this so that our change in energy equals power times the change in time. And so that, there's our integral, that our change in energy is going to equal the integral of power times time, or P delta T, which is our watts. It's watts seconds, which is also just a joule per second times a second, which gives us joules. Now, PG&E, when they sell us energy, and that's what they do, they sell us energy, they don't sell us power, although they call it power, and we get the PG&E bill, and we call it the power bill, but it's really the energy bill. Okay. PG&E sells us energy in kilowatt hours. Now, a kilowatt hour in kWh, so 1 kilowatt hour, okay, if we do this conversion, this is how many joules it's going to be, and it winds up being 3.6 megajoules, which really would be, a megajoule would be a more, shall we say, consistent unit with those of us that truly study energy. But we use the English system, and this is what they like, and it just makes sense. It makes sense to the power company that they put it in units of kilowatt hours. Now, there's another a unit of power that you guys may have heard of, and it's called the horsepower. And anymore, it is actually defined as 746 watts. And that's about where we're going to finish. The 1 horsepower equals 746 watts. In fact, all of our English measurements, which are 1 inch, is defined as 2.54 centimeters. That's the definition of in 1 inch, and 1 foot is 12 of those. So all of our English definitions are now defined by metrics. But that's power. We talked about friction earlier. And that's really all you guys are going to need to finish your work for today.